In this video, I'm going to show you how to solve this vibration problem with the Fourier series method for a damped structure, damped at 10% viscous damping, and we're given the mass and the stiffness, and the force will first be decomposed into a Fourier series, and then we're going to use its Fourier coefficients to let us compute the solution. And let's first take a look at the formulas that we're going to use. So we have these Fourier coefficients and the Fourier series for the force. And also we're going to use this solution for the steady state vibration of a damped structure, damped at some zeta value. And notice that here we have both AN and BN appearing. So let me share the other software. I'm going to use the TI Nspire, on which I have already stored the formulas for my A sub n, B sub n, and the Fourier series, and the beta sub n, which is basically just the end frequency ratio between the driving force and the natural frequency of the structure. And here I have also the formula that I just showed you, which is the damped solution for the single degree of freedom structure. All of these are in comments, so nothing is really defined or stored into variables yet. So let us proceed to solve the problem. So first, what I do is usually I clear all my variables to make sure they're clean. And also I have two variables that are 2 letters. So let me delete variable for P0 and T sub P, namely the force amplitude and the period of the force. Right, so with that being done, I'm going to first input my force, which is needed in those Fourier integrals. So let's take a look at it again. The force is like this, which means it's linearly increasing for just half a period, and then it disappears for half a period. So I'm going to write it like this. This is only valid, of course, when it's non-zero. So it's P naught, be careful with the spelling, times T, it's a linearly increasing function, divided into, be careful here, TP over 2. So when time hits TP over 2, it reaches its maximum. And then, of course, it goes to 0 for half a period. And my omega will be, of course, just 2 pi over T sub P. So let me type that as W. Okay, that's for my omega. It is 2 times pi over T sub P. All right. Now I'm going to use my AN formula. So let me pull it down from the above and remove the comment sign so that I really get some integration done. Of course, I have already defined my force, so I'm going to integrate it to T sub P over 2. Okay, be careful here. That's not generally true, but true in this problem because outside of that I have 0. So that is my A sub n. Well, first let's check the seemingly problematic case where n is 0, since you have something like 0 over 0. So AN, given that n is 0, seems to be undefined. However, we can use the limit command, which is under this template key. I'll have a limit command, let n approach 0, and let's see what happens to AN. In fact, it gives us a non-zero value, so I'm going to store that into a 0. Okay. then I know that for other n's, basically this is a -1 to the nth power. So if n is even, that's going to give me 1 minus 1, which gives me 0. So I know I don't need the even n's. So let me write down my general formula for the a coefficients like this. It will depend on the given index, and I'm going to use a useful when function. So first I'm going to check a condition, whether this n is even. So I'm going to check if n over 2 equals integer value of n over 2. If it's true, then I know I need no coefficient, it's 0. If it's not true, that means it's odd. Then I've got -1 here, another -1. So that's -2, of course, sine n pi 0. So in that case, in the case where it's odd, let us have a result of -2 times p0, as you pick up from here, from these two terms, and the p0 over n squared pi squared. So that's going to be my general a sub n. So that's done. Let's proceed to calculate the b sub n's. So again, let's be careful. This formula is true because I have a piece of the force being 0 during the second half period. So I just need to do this integral from 0 to tp over 2 for my bn. And this is my result. And it's quite transparent, sine n pi 0. And I can just put in my b formula, which will take the user input of n value and calculate the simplified expression from the above. So it's going to be a quotient. It's going to be a negative, and then n times -1 to the n power. So n times, -1 raised to the nth power. And then you have something left. Here is pi and p naught. So let's put that in. It's multiplied to pi and p naught. Over n squared and pi squared again. Right. And then we can assemble the Fourier series by defining a function called fs as the Fourier series for the force. It will require the user to input the maximum n you want to go up to, and it will start with a0 over 2, and then let the counter go from 1 to the maximum n given, and compute the series as given in the Fourier series formula. So the maximum j will be given n. So that just defines a function that we can use later. But now let us proceed to solve the vibration problem. Okay, so we're going to put in all these parameters, the mass, stiffness, zeta. So zeta is equal to 0.1, 10%. K, the stiffness in newtons per meter, is going to be 210. And because it's kilonewtons, so 3 more zeros. And then it's per mm, so 3 more zeros to bring it to Newton per meter. And then my mass is given as this number. And then the P naught, the amplitude of the force, is on 178,000 newtons. And then the period is 1 second. And let's also calculate the natural frequency, which is square root of k over m. If you don't like that number, you can use Control Enter. So now I'm ready to use the solution that I wrote down earlier as a comment. Now let me remove the comment sign so that I actually have a Fourier series for the solution. Actually, sorry about that. I need to also define my beta sub n first. I need this line first because that appears in the series solution. Okay, so that defines beta sub n. And now let me pull down that formula for the series solution to the vibration problem. Remove the comment sign. So let's try it. XS allows me to enter some maximum n. Let's say we want to go up to 10 being the maximum n. So see, it's a function of t because I have given all the other parameters, numerical values. So now let's try and plot this thing, this solution. Actually, I'm going to plot it for n max being 20. So let me do it like this. X20, the thing I'm going to plot is going to be, first of all, I assemble a series solution for n going up to 20. But also you notice that it's a function of time, but on this calculator, it plots functions of x. So I need to change all my t variables to x. And also let me trim the left-hand side because there is no vibration when time is negative. The problem hasn't started yet. So let's attach this trimming function using when x is smaller than 0, then I need nothing. So give me a 0. Otherwise, give me 100% of what's attached, being the series solution here. Okay, so that's my x20. Okay, this is ready to be plotted. So let me insert a new page as a graph and plot this thing. Oops, okay. So it's called x20. It doesn't show up too well. Let's just zoom in. And you can use this tools button. Zoom, perhaps let's do a zoom fit first. And then zoom onto the appropriate areas. Let's just see a few ups and downs. All right, so that's the vibration history. Let's check some maximums by using analyze graph maximum. You can have more digits if you like by pressing menu settings. Let's perhaps go back to the calculator view. Menu settings. A few more digits. Okay. So that is the vibration history. Perhaps let's do it in millimeters. Okay, sorry, I forgot about that. So multiply this meter value to 1,000, so I get just easier numbers to look at. So let's zoom fit again. All right. So we see the maximum vibration or amplitude is about 9.8 millimeters, happening at about 0.5 seconds. We can also check the minimum here. Okay. What we can also do, of course, is plot the Fourier series. Let's not forget that we did assemble this in a function called fs, this one. So let's take a look at it. So fs, let's also go to 20 terms, let's say. It is, again, you see, a function of time. So let us define a variable called f20. It's when x is smaller than 0. I don't want anything, otherwise give me a 1. That's to trim the function, and then multiply to fs. with 20 terms, but of course we need to change all the t to x again. Let's plot it. Let's insert another, actually I have an empty graph here. So fs of 20. Oops, so let me go back and check that. It's called F20, sorry about that. Control G. It's called F20. So again, you can use zoom fit, let's say, followed by some, let's say, zoom box. See a few ups and downs. So you see that definitely does look like the original function. Let's check the maximum. Well, it overshoots a little bit, or undershoots. Let's go back and check. It's 178, so it's overshooting a little bit here. And we also see this Gibbs phenomenon here. Let's also check where it crosses 0 to make sure it's not doing something too crazy. This should be at about 0.5. So it is at 0.54 seconds. So of course, this is not all that smooth because we don't have that many terms, and also because it is a discontinuous function that we are approximating with a Fourier series. So in any case, we do get good results fast using a CAS calculator. So thank you for watching.